Okay, so what we're going to do is we're going to walk through the extended theory paper, question by question. Obviously the idea with this is it's a video, so you can jump forward, rewind, and basically just get to the questions you need to be looking at. As we do this, I'm going to be explaining how I would approach each question, and then telling you what would count as an answer and what would not. Okay, so we jump straight in. Our first question is a definition question. We're saying to define acceleration. Okay, now I know that acceleration is something to do with something that's moving, and I should remember that it's to do with something changing speed, right? The answer to changing speed is not enough, and it has to be to do with how quickly it's changing speed. So the correct answer is the rate of change of speed. Okay, that means that saying a change in as in an increase or a decrease is not going to be correct. Okay, it has to be a general change. Saying the rate of increase of speed is wrong. If I'm not sure about that answer, instead I could have put that as an equation. So if I wanted to write the equation for acceleration, I could have written acceleration is the change in speed divided by time. Okay, so that would have been fine as well. Question 1b. So we have a car, and we know that it is starting from rest, okay? Remember, rest means it is stationary. So time 0, we know it is stationary, which means it is here, at 0 speed. It now tells us that it's going to go from 0 to 15 seconds. So I immediately know I'm going from 0 to 15. 1, 2, 3, 4, 5. There. That is my 15-second mark. Okay? And it has a constant acceleration of 28, up to a speed of 28 meters per second. So I'm going to go up 10, 20, 1, 2, 3, 4, 5, 6, 7, 8. Here. Okay? And what I need is a point where those two meet, so I can go up. So it's up here somewhere, and across. And I know that my point is here. Okay? So I know I'm going from 0 up to there. What I can then do is join those two up using a straight line. Okay. Here we go. That's nice and simple. Okay. Because this is a graphing question, I need to make sure my lines are straight, and I'm using a ruler. Pencil or pen doesn't matter, but pen would be preferable because you can rub it out. Okay. So that's my first mark. Second mark. I'm now going from 15 seconds up to 32 seconds. So here's 30, 1, 2, there. And it has a constant speed. That means the speed is not changing. So that line coming across here is going to have to be at 28 the whole time. So I'm going from here straight across till we get to 32, which was there. So I'm going to join those 2 points up. Okay, along to that point. There. Brilliant. So that is the first 2 marks done. It's a 5-mark question, so these next 3 marks are going to come from this section here because there's a calculation involved. Okay? We're supposed to put any calculations we're doing in the space below here, so it needs to be in this space down here. When marking it, if you got the right answer, I didn't bother giving you marks for this bit. I was checking your workings. If you get the right answer, you get the marks. But it's worth doing them just in case. So we know it's going from 32 seconds until it comes to rest. Okay? And it's getting slower by 2 meters per second squared. Okay? Every second. So that means I'm losing 2 meters per second every second. Right? So I need to know how long is it going to take me to go from 28 meters per second to 0 meters per second if I'm losing 2 every time. Okay, so I'm going 28, 26, 24, 22, down like that. What that means is I can actually use this equation here that we had at the start. So the equation was A is change in V over T. Okay, I'm trying to work out T, so I'm going to rearrange this. So I'm going to bring the T up, so it's now T times A is the change in V, and I can bring the A down. So T is change in V divided by A. So that's what I'm going to do. The change in V is from 28 to 0. Well, that's 28. So 28 divided by the acceleration. The question told us that was 2 meters per second. So that is 2. 28 divided by 2 is 14. So I know this takes me 14 seconds. What I can now do is I can count across from 32. So 32, 42, let's add 10, 11, 12, 13, 14. I'm on 46, so that has to be on 46 there. If it is anywhere else, you are not going to get the marks. Once I've done that, I can join up the 2 points. Done. Okay. That last bit is worth 3 marks. And that is that section. Okay. Part 2 of question 1b. From the time 15 seconds to 32 seconds, it is saying that the car is moving in a circle, right? That means it is going around like this. Maybe not all the way, but it's going in that kind of path, right? Now, the question is, what direction is the resultant force on the car? Okay, the car is turning towards the center of the circle. Okay, now I don't know if that's left or right. It could be a circle going clockwise or anti-clockwise, so I can't say left or right. I need to say relative to the circle, or which way is that force going, because that's the only thing I know about. So the question is the force going forwards, backwards, outside the circle, or into the center of the circle? If I want something to turn into a circle, something has to be pulling it inwards. Think about if you swing something around your head, the string that you're swinging it with, that is going to be pulling it towards the center. So here we have a force pulling the car towards the center of the circle to make it turn. Okay, so that is my answer. The direction of the force is towards the center of the circle. Okay, not left, not right, it has to be towards the center. Part 2, what happens to the velocity of the car? Now, they've said velocity here, not speed. Okay, so before, when we were looking at this graph, it told us that it had a constant speed. So we know that the number isn't changing. It's always 28 meters per second. So this is a velocity. Velocity is a vector, which means it must have a direction as well. Is the direction of this car changing? Yes, because it is moving in a circle. It's not going in a straight line. So what happens to the velocity of the car? It changes. And I might add to that, it changes constantly, just to be really clear. But it's changing all the time. And that's that question done. 1 done. Question 2. A force is used to move an object from the Earth's surface to a greater height. Explain why the gravitational potential energy of the object increases. Okay, so the first thing I need to be saying to make this clear is what is gravitational potential energy. Just like before, when I did my acceleration question here, I could use an equation. I can do the same here. So, my equation for gravitational potential energy is the mass of the object times the gravity of the object times the height of the object. Okay, so I'm showing that gravitational potential energy depends on the height of the object. What I can then do is say that if the height gets bigger, that means the gravitational potential energy is also going to have to get bigger. So as height increases, GPE increases. It's alright for me to use the abbreviation because they use the abbreviation in the question. If I didn't have that in the question, I could still use it, but I'd have to say what it means. Question 2b. This picture shows a train moving up towards the top of a mountain. The train is transporting 80 people. Okay, so that's a key fact. 80 people. Each has a mass of 65 kilograms, and it is rising up a vertical height of 1,600 meters. Calculate the total increase in gravitational potential energy of the passengers. And that is plural. It's all the passengers. So I'm going to use the equation I had here. So GPE is mass times gravity times height. Now I can plug those numbers in. So the mass was 65. Gravity, they haven't told me it, so I can just say 10. 10 is fine. If you want to be precise, you can use 9.81, but 10 will do. 65 times 10 times the height, that's 1,600 meters. If I do that on my calculator, gone 65 times 10 times 1,600 that is 1,040,000. 1,040,000. Okay, that answer is not done because it's for all the passengers, we said, and there's 80 of them. So I need to times that answer by 80. Okay, so I've now gone 1,040,000 times 80 is 832,023,4 5 zeros. Okay, that is my answer. It's not complete though, because this here has not got a unit with it. That's where that second marker is going to come from. So I need to put a unit with this. This is energy, so my unit is joules. And what I want to do is I want to make it really clear that that is my answer. So I'm going to put a box around it. Okay, so if you're doing a calculation like this, where you've got lots of workings, put a box or something around your answer to make sure it's clear that is your answer. Right. Question 2C. The engine of the train has a power of 1,500 kilowatts. The time taken to reach the top is 30 minutes. Calculate the efficiency of the train, or of the mountain, of the engine going up the mountain. Okay, so I previously had an energy on this page here. So I have a choice. Either I can turn that energy into a power and then compare the powers, or I can turn this power into an energy and compare the energies. It doesn't matter which you do, you'll get the same answer. I'm going to turn this power into an energy, I think that'll be easier to do. So, remember the equation for power is power equals energy divided by time. So if I turn this into energy equals something, it's going to be energy is power times time, and I can plug that all in. So 1,500 kilowatts, or kilowatts is thousands, so that means 3 more zeros, times by 30 minutes, but 30 minutes is in minutes, I want it in seconds. So I'm going to times that by 60, because there's 60 seconds in every minute. If I do that on my calculator, I go 1,500,100 times 30 times 60 is a big number. It is 2, 7, 1, 2, 3, 4, 5, 6, 7, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So that is the amount of energy that that engine is using. Now, remember the efficiency of something is the output we have divided by the input. So I need to do the output, which was what I calculated on the previous page here, because that was the amount of energy that was being put into those people to make them lift up. So that was 832. And then 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5. I'm going to divide that by 27 and 1, 2, 3, 4, 5, 6, 7, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Let's do that. So 832, 0, 0, 0, 0, 0, divided by 27, 1, 2, 3, 4, 5, 6, 7, 8. If I do that, I get some kind of number here. If it comes up like this on a calculator, press this button here, SD, and that's going to turn it into a decimal. So I've got 0.03 ... Don't care about the rest. Okay, that is an efficiency already. I could leave it as a decimal like that, but I prefer personally percentages, so I'm going to turn that into percentage by timesing it by 100. Okay, so I do that. That is now 3%, and that's going to be my marks. You can leave it as the 0.03 if you want and put 0.03. If you're going to write it as a percentage, make sure you put that percent sign. If you don't put the percent sign, they'll assume it's still this. If you're doing this kind of calculation, there's a lot of places you can get mixed up because there's lots of zeros, you might get these numbers back to front, so there's one very quick way to check. Efficiency can never be more than 100%. Okay, 100% is the maximum efficiency you can ever have. And in fact, you'll probably never even get 100% efficiency. It will usually be less. So if your answer here comes out as something different, say it came out as 2700%, if you get something like that, that is definitely wrong. So don't do that. Okay, anything that is more than 100 is wrong. Correct it. Check it. Okay. Question 3. Complete the statement by writing in the blank spaces. The moment of a force about a pivot is equal to something multiplied by something. So I can have these either way around because it's going to work either way. It's the same for the calculation. So I'm going to say it's equal to the force. Remember, a moment is a force that is being applied to some kind of object when it's turning. So it's going to be the force multiplied by the distance from the pivot. Okay, it could be from the axis or from the turning point or from the fulcrum, as another word you can use. Technically, it should be perpendicular, but for today's test or this test, I let that slide. Okay, so it's the distance from the pivot. And again, either way around is fine. You need both to get the mark. Second question. The figure shows a horizontal rod of length 2.4 with a weight of 160. Okay, so these are numbers that I might be having to use later, so I'm going to highlight those, make sure I'm aware of them. The weight of the rod acts at the center. So I know the weight is acting here. Okay, so I know this is the center. The rod is suspended by 2 vertical ropes, X and Y. The tension in each rope is 80. So that's there, and that's here and here. Okay. Give the name which is given to the point at which the weight acts on the rod. Well, they already told me that this is it here, and they told us it is the center. Okay, so it is the center. Is it just center? No, it's the center of mass. Okay, you can also call it the center of gravity, but one or the other. Okay, the middle doesn't count, the weight doesn't count. It has to be the center of mass or the center of gravity. Once we've done that, we can now work out what the mass is for this question. Okay, a few people were getting confused. You were trying to multiply 2.4 by 160 because you were trying to calculate the moment. This question is asking for mass. Okay, so remember, mass comes from the weight equation, which is weight is mass times gravity. I want to get this bit, so I'm going to rearrange it. So I'm going to have that the mass is the weight divided by gravity, like this. And then I can just put the numbers in. So I've got the weight is 160. I'm going to keep using 10 for my unit, for my gravity. So 160 divided by 10 is 16. Again, I need the units on this. There's no units in this space, so I have to have the units to get the mark. The unit of mass is kilograms. Question 3b, part 3. Now, we're going back to our picture of the rod and it's saying that this rod is in equilibrium. Using the information in this picture, we have to say why, right? And the key here is this is a 4-mark question. So it can't be as simple as 1 or 2 sentences. There must be more going on. So let's talk about equilibrium. There are 2 types of equilibrium. The first one is to do what we were talking about here, to do with moments, right? So this picture has got the same moment on each side. The moment going up on the left, which is clockwise, is the same as the moment going up on the right, which is anti-clockwise. So those 2 moments are the same size, meaning they cancel out and there is no overall moment. Okay, that is our first mark, or first 2 marks. So the clockwise moment, we say clockwise because it's going to make it turn in a clockwise direction. Clockwise, remember, means this one here, that's clockwise, this one's anti-clockwise. So the clockwise moment equals 80 newtons times by 2.4 meters. And I can work out what that is because I want to be showing as much information as I can. So 80 times 2.4 is 192 Newton meters. The anti-clockwise moment is also 192 Newton meters. Therefore, the moments are in equilibrium. That's 2 of my marks. Okay, because I've only said 2 things. I've only said clockwise and anti-clockwise. Okay, I still need to get 2 more marks. So let's go back to the picture. There's something they've included in this picture that we haven't talked about in this question. That is this force here. Right, this force is pulling it downwards, which means if it's not balanced, it's going to make this rod accelerate in the downwards direction. But we've got a force here pulling up and a force here pulling up. So we can see that these 2 are 80. 80 plus 80 is 160. Well, there's 160 up and 160 down. Now they're the same, it's balanced. That means it's in equilibrium in that sense as well. So that is our second part of the question. The downward weight equals 160 newtons. The upward tension is also 160 newtons. Really, I should write 80 plus 80 is 160, but we've just done that, so that's okay. Therefore, the forces are balanced. Done. 4 marks. Excellent. That is that question done. That's brilliant. What we're going to move on to now then is onto a question about thermodynamics. So the picture shows a cold plastic spoon. Okay, the fact it's plastic is going to be important later. So let's get that highlighted. That has just been placed in a hot liquid in a cup. So there's hot liquid in here. Describe in terms of molecules why the temperature of the whole spoon increases. Okay, we want to talk about the whole thing, so this section up here as well as down the bottom. And it is 3 marks. Okay, so if it's 3 marks, I need to be saying three things. So first of all, I need to say how the heat is getting in from the particles. Second, I need to say what that does to the particles. And then third, I need to say how that heat moves up the spoon. Okay, so the first thing is how are these particles transferring heat from the outside to the inside. One or two people said that the particles actually go inside the spoon. That's not correct. Okay, the key thing is that the liquid particles collide with the spoon. Okay, they're actually bouncing off it all the time. Okay, that's our first mark. We've said what happens there. Now we're going to say what happens to the particles inside. This transfers energy. So you could say transfers heat, transfers kinetic energy to the particles, something about them gaining the energy from the liquid. So this transfers energy to the particles in the spoon. That's 2 marks. For our third mark, we need to be saying how that then moves up the spoon. Okay, so this makes them vibrate more. Remember, it doesn't just make them vibrate, they have to they're already vibrating, so they're vibrating more than they were before, and transfer the heat to their neighbours. And that is our third mark. We've said how it gets in, what it does, and how it moves up. 3 marks. Question 4b. Okay, that was a plastic spoon. We're now replacing it with a metal spoon. Describe an additional process, so it's a different one to the one we just talked about, by which the temperature of the whole spoon is increased. So, we just talked about plastic, and remember plastic is a standard solid where the particles are going to vibrate, and then they're going to transfer the energy from particle to particle like this. Particle moves along, the energy moves along like that through the particles. In metals, there's an extra thing that can happen. Remember, metals have free electrons that aren't doing anything. They're not attached to atoms. So if we now add heat, those electrons can carry the heat through the material. That's the difference. That's why it's key that this is a metal spoon, not a plastic spoon. So what we need to be saying is that the metal contains, the best phrase to use is delocalized electrons, but you can also just call them free electrons. Free electrons is fine. So that's 1 mark. These can move and carry the heat through the spoon. There you go. So that's the question B. Question C. The cup contains 150 grams of liquid with a specific heat capacity of 4.2. When the cold spoon is placed in a hot liquid, the temperature of the liquid decreases from 80 to 56 degrees centigrade. Calculate the loss of thermal energy from the liquid. So we're working out how much energy came out of the liquid into the spoon, right? For this, we are going to need our specific heat capacity equation, which is specific heat capacity, that's energy, is the mass times the specific heat capacity times the change in temperature. Okay, so let's look at the question. We have 150 grams, we have a specific heat capacity there of 4.2, a starting temperature of 80 and end temperature of 56. So let's very quickly just check the units. This mass here is in grams. Normally, I would want that to be in kilograms because mass should always be used in kilograms, but our specific heat capacity is also in grams. So the fact that they're both in grams means that it's okay. It's still going to work. So we can use those numbers as they are. So when we do this, I'm going to do 150 times by 4.2 times by the change in temperature. So I've got 80 minus 56 is 24 degrees C. So 150 times 4.2 times by 24, get my calculator, 150 times 4.2 times 24, that is 15,120. And that is my answer, 15120. But again, there's no unit, so I need to put the unit in. This is an energy, because we're working out the thermal energy, which means the unit is joules. Done. Question 5. For this question, I think a lot of people seem to skip reading this. I don't know why you decided not to. Maybe you were getting tired, maybe you were confused, but it is very key that you look at what is happening in this explanation, because that is going to affect what we see happening in our question. So we have a apparatus, which just means some equipment, used to observe the motion of smoke particles that are in the air in the box. Okay, so there are smoke particles in this box here. Okay, and what we're doing is we're looking through a microscope into the box. Notice how we're looking from the top, right? We're looking from above. The light of the lamp enters the box through a window to the side, so the light's coming in there, and the smoke particles are being observed using the microscope here. Okay, the question is, the motion of a single smoke particle can be observed through the microscope. In the circle shown, sketch the path of the smoke particle. So it is just one particle, okay, which means I shouldn't be drawing any kind of smoke lines or anything like that. It is one particle. So I'm going to draw my particle there. And then a few of you drew it moving upwards like that. And I can see why you did that, because you've said that hot gases rise, which is true. But remember, we're looking from the top. That means we're already above it. If it was rising, we'd see it coming straight towards us. So that's clearly not the case, because we can't draw something coming towards us. They wouldn't ask us to try and do something like that. What we are being asked to draw is how that particle moves side to side. And this is all to do with Brownian motion, remember. It's to do with the way the particle bounces around because of the other particles colliding with them. So this particle is going to be moving, and then when it gets hit, it's going to be changing path very suddenly. Okay? It's going to be going in a random kind of pattern like this. It doesn't matter exactly what it looks like, as long as it is sharp corners, straight lines, and seemingly random, like that. Okay, the lines can overlap, that's okay as well, but they mustn't be curved. They have to be straight, the corners have to be sharp, and it has to go in a kind of random pattern. If you've drawn it bouncing from side to side like this against the edges, that's wrong, because that's just the window you're looking through in the bottom of the microscope. It could technically leave the container, the view, sorry, and then come back in. Okay, so that's what you need to have done for this question. Now we need to explain why it does that, right? So remember, this is all to do with Brownian motion. So the first thing we need to say that this is Brownian motion, okay? So if I go, this is Brownian motion. If I've mentioned Brownian motion anywhere in my answer, I get a mark. But the question is, what does that actually mean? So what is happening is this smoke particle is being bombarded by other particles. It's colliding with gas particles in the air. Okay, so the answer is gas particles in the air collide with the smoke. That's another mark. So we've explained what is making it change direction. We now need to explain why it has got this kind of path, okay? So we need to say that the particles are moving randomly. The particles move randomly. And that is explaining why it is bouncing around in all these kind of funny directions. It's not a nice continuous path. And that is our answer for that bit. That's 3 marks there, okay? And you could have said those things in any order. You could have said the random bit first, you could have Brownian motion last. Doesn't make any difference, okay? Now what we have last is seemingly a very different kind of question, right? We're now talking about tennis balls instead of a gas. The link is that the tennis balls are hitting the side of a container, the side of a box, which is just like the gas particles inside the box bouncing against the side of that as well. Okay, so there is a link between these two topics, but it doesn't really matter. What matters is the equation they're going to ask us to use. So, a tennis player is practicing by hitting a ball many times against a wall. It hits the ball 20 times in a minute, in 60 seconds. The average change in momentum for each collision is 4.2 kilogram meters per second. Calculate the average force exerted on the wall, sorry. So, I've got here this funny unit. The question is, what's that a unit of? Because that's going to give me a hint about how to answer this question. So it's kilograms meters per second. I know meters per second is speed, right? I know that's that. I know kilograms is a mass. So it's a mass and a speed. It's momentum. This is momentum. It actually told us that in the question, right? So if I'm talking about change in momentum, I should immediately be thinking, that's impulses. So my impulse equation is the force is the change in momentum, and that's divided by the time. Okay? So, what we then need to do is put the numbers in. So we've got 4.2 and 60. So if we do that, 4.2 times 60, 4.2 divided by 60, careful there, that is 0.07. It's a force, so that needs to be newtons. But I've only done that for one collision, right? We're saying there's 20 collisions, so there's 20 lots of this in our time. So that is 0.07 times 20. If I do that, I get 1.4, and it's still newtons. So that is my answer, 1.4 newtons. Again, I need to have that unit there to get my marks. Okay, and that's the 3 marks. We're doing well, we're nearly there. Question 6. So, question 6 is about an energy source. And it says the diagram is a simplified diagram of geothermal power stations. Okay, so this here is a geothermal power station. Describe the energy resource labeled X, which is here. Okay, this is X, right? So I need to work out what is this source of energy. Now I can see in the picture they're pumping water down underground to get the energy from it. So the energy is being absorbed by the water and taken up. Okay? So the clue for what the energy is the name, right? This is called geothermal power. So hopefully you remember what the source is already. But we need to, if you don't, there's a way of working it out. A few people put geothermal as their answer. They said it is geothermal energy. That is not correct. Remember, geothermal is the energy source, not the actual resource down here that's giving us the energy. Okay, this is the type of energy that power station that we have, right? So if you put geothermal here, what you're simply saying is that this is geothermal, which is wrong. Okay. The answer is breaking down this name. Remember, geo means rock. Yep. Thermal means heat. So we're getting heat from rocks, so that must mean we have hot rocks. Okay. So that works fine as your answer. If you said heat from inside the earth, that would be okay. It's a bit vague, so try and stick to hot rocks in this case. Question B. Identify the useful energy transformation which takes place in the geothermal power station. Tick one box in each column. That is key. It is one box you are ticking on each side. If you ticked more than one box, you are a ninny, because that's just wasting marks. Okay? So, what is the input energy? Well, we just said it is from hot rocks, so we know it's to do with heat. It's also got the word in the name, it's thermal, so we just go, there's thermal, that's my answer. The output energy, well, remember it's a power station. Power stations generate electricity, because that's what we're going to use in our homes. So the answer is electricity. We now switch to a different energy source. So it's two disadvantages of getting energy from fossil fuels. Okay, so be really clear that that's the energy source we're now talking about. Okay, there's a few different things you could have put for this. The two obvious ones are, first, this is non-renewable. Okay, anything about it being non-renewable or going to run out or being a limited resource, that is fine. Okay. The second mark could be that it releases greenhouse gases. Greenhouse gases. Okay. You could change that slightly, so you could say it causes global warming because of the greenhouse gases. That's okay. You could say it causes climate change. That's fine. In this case, it also allows you to say causes atmospheric pollution or air pollution. I would be very careful about using the answer air pollution, because sometimes they get a bit picky about the word pollution. So just as a piece of advice, I would say avoid the word pollution, be specific, talk about the type of pollution, which in this case is greenhouse gases. Let's be very, very clear. Fossil fuels do not cause the hole in the ozone layer. That is a different thing. Okay, so it's not that. We're not interested in acid rain or any of the other things. It's just the greenhouse gases for fossil fuels in this case. Okay, so that is our 2 marks there. Question 7. So here we're going back to momentum. So explain why momentum is a vector quantity. And so many of us were really close with this. So we go back to our definition of a vector. Remember, a vector, vectors have size, we know, and distance is what a lot of you put. I don't know why you put distance. I don't know if you were just getting confused about the words or if you were thinking about another question. It's not distance, it is direction. Okay. A vector has size and direction. It is that direction that is going to get you the mark. Okay, so make sure that you have put that. Here, we're now going to talk about momentum. So, the crumple zone at the front of the car is designed to collapse during a collision. Okay, so it's this part of the car here, and when the car hits the wall, it squashes. And by squashing, it is absorbing some of the energy. It's also increasing the impact time. Remember, if we increase the impact time, that is going to decrease the force, because it's our impulse equation that we used in the previous question about the tennis balls. So, in a laboratory test, the car of mass 1,200 kilograms, it's a number, let's highlight it, is driven into a concrete wall. A video recording of this test shows that the car is brought to rest in 0.36 seconds. So I've got a mass, I've got a time, I can probably see where this is going. When it collides with the wall, the speed of the car before the collision is 7.5 meters per second. Calculate the change in momentum of the car. So, remember let's not even worry about the change bit first, let's just do momentum. So the momentum, remember, is the mass times the velocity. Okay, it's mass times velocity. So the momentum of that car before the collision is 1,200 times 7.5. If I do that, I am going to get 9,000. 9,000, what's the unit? Kilograms, meters per second. So that's the starting momentum when it was moving. We've said that it drives into the concrete wall, so it's going to stop, right? It's going to come to a complete standstill. That means the speed will be 0. If the speed is 0, what is the momentum at the end? It is 0 as well. So the question is, what's the change momentum from 9,000 to 0? That's 9,000, right? So the answer is 9,000 kilogram meters per second. I haven't used the time yet. I don't need to use that for this part of the question. That's for later. We're going to use it on this part of the question. So we're using our impulse equation again. So it is the force is the change in momentum divided by the time. So we said the change in momentum was 9,000. The time was, what did it say? 0.36. 0.36, that was seconds, right? Just check. Yep, that is seconds, so the unit is fine. We don't need to change it. So we got 9,000 divided by 0.36 is 25000. 25,000. That's force, so the unit is newtons. And that's the answer, that's the end. So 25,000 newtons. Done. Last question, no, second to last question. C. A different car has a mass of 15,000 kilograms. The last one was 12,000 kilograms, so this one is heavier. It's a bigger car, so it's probably a truck or something like that. It collides with the same wall, and all of the energy is transferred to the collision, is absorbed by the crumple zone. Okay, so all of that energy is still being absorbed. The energy absorbed by the crumple zone is 4.3 times 10 to the 5 joules. Show that the speed of the car before the collision is 24 meters per second. So, this is probably the hardest question in the paper because it's a show that question, which means they haven't given you any direction about what to do. You're trying to prove it for yourself. And more importantly, because it's a show that question, you need to be answering it in a way that is clear and it's explaining to the person reading the answer what you've done. So for a start, if you've just written a bunch of numbers and not shown what you're actually doing, you're not going to get marks for this. Now, working out what you actually have to do, what I should be looking at as I go, well, I've got a speed. Okay, I know there's a speed there, and I know I've got an energy. Okay, so what is the energy that's to do with speed? That's kinetic energy, right? So what this question is saying is all the kinetic energy that the car had was absorbed by the crumple zone, right? We've been told that the energy that was absorbed was 4.3 times 10 to the 5 joules. So if I can show that the kinetic energy was 4.3 times 10 to the 5 joules, then I've got proof that this was going 24 meters per second. Okay. I can do this two ways. I can either start with the energy and try and work backwards to get the speed that it was moving, or I can start with the speed and try and work to the energy. The equation for kinetic energy is the mass times the speed squared divided by 2. You can rearrange that to get it as speed equals something and then put the energy into that equation and try and work it out. Because it's a bit of a fiddly equation to try and reorganize, I think it's probably the safest thing to do is just to stick this 24 meters per second in here and see if the energy it gives me is the right energy. Okay, so I'm saying my kinetic energy is this. This is my equation. So let's go, the mass is 1,500 kilograms. The speed was 24 meters per second. So the energy is going to be 1,500 times by 24 squared divided by 2. We can do that on a calculator. You can try and type it all in at once. I think it's probably best to do it in steps. So I'm going to do my 24 squared first, just to be safe, so I don't accidentally square something I don't want. 24 squared is 576. Now I'm going to times that by the 1,500, which gives me a big number that I'm not too worried about what it is because it's not my answer yet. Once I've done that bit now, I'm going to divide by 2. And I get 432,000. Okay, that's an energy, so that is joules. My energy I'm trying to work out is 4.3 times 10 to the 5. So remember, 10 to the 5 means that this decimal point has 5 places after it before you get to my smallest unit, right? So if I rewrite this without the times 10 to the 5, I'm going to get energy absorbed is 430,000, because I've gone decimal point 1, 2, 3, 4, 5, that's the end of it, joules. The kinetic energy is 432,000 joules, and you can see these two numbers are very similar. Okay, there's only a 2,000 difference between them, right? Which I know is a big number, but in the scale of these numbers, in the grand scheme of things, it's pretty similar. So I'm going to say similar. Therefore, V equals 24 meters per second. And you can see, because it's a show that question, I'm actually saying what my answer is. I'm saying, look, I've shown that this is 24 by comparing these two numbers. That's how you get these marks in a show that question, because you're actually drawing the reader's attention into the fact that it's this answer. Whew. Final question. Suggest what would happen to the car if it is traveling faster than 24 meters per second when it hits the wall. Okay. Now we've said that all the energy was absorbed before, so the reasonable guess would be to say that not all the energy was absorbed, right? Unfortunately, that's not the answer, because that doesn't tell us what happens to the car. So the question is, what would happen to the car if all the energy was not absorbed? Well, the energy is going to go somewhere, right? So it's going to go into a different part of the car, and it's going to damage it. Okay, it's going to change the shape of it just like it did this crumple zone. So we might get some bending in the chassis underneath, or some breaking of the windows, something like that. Okay, so as a general answer, I'm going to say other parts of the car might be damaged. Okay, you can see I'm being very careful with my language here. Okay, I'm being vague about which part of the car, because I don't know which part of the car it's going to be, but I know it's going to happen somewhere. But I've specifically said what's going to happen to them. I've said damaged, okay? Because a lot of you said the car would be destroyed. Okay, now remember, destroyed means completely broken apart, unusable, shattered into 1,000 pieces kind of thing, right? I haven't been told how much faster it's going. It could be going 25 meters per second squared. 25 meters per second, sorry. If it's only going 1 mile an hour faster, 1 meter per second faster, that means the change in the amount of damage done is not going to be that big. Okay, it's not that 1 extra mile an hour, 1 meter per second more is going to suddenly make the car explode. Right, that's not going to happen. So I need to tone back the language there and be scientific about it. I'm just going to say it's being damaged, and that's my answer. And there you go. That is this full paper. Hopefully that was helpful. Use this to review your answers, make sure you answer them correctly. What we're then going to do is you're going to use this to complete the reflection sheet. So you need to be going through the questions, working out which questions were the ones where you needed to go through and earn those marks, which ones you need to do more revision on, and which ones you need to practice on over your summer break to make sure you're ready when you come back after the summer holidays. Thank you.